Welcome back. In this lecture, we will discuss a widely used numerical method called interpolation. First of all, let us see what is interpolation. Interpolation is the process of estimating unknown values that falls between known values. We are given the values of a function at different points x0, x1, etc., xn. We want to find approximate values of the function for new x's that lie between these points for which the function values are given. This process is called interpolation. Let f0 is equal to f of x0, f1 is equal to f of x1, etc. fn is equal to f of xn be the values of an unknown function measured at x0, x1, etc. xn be available. The idea in interpolation is to find a polynomial Pnx of degree n or less so that Pn of x0 is equal to f of 0, Pn of x1 is equal to f1, etc. Pn of xn is equal to fn. That is, the fitted polynomial is agreeing with the unknown function at the data points x0 f(x0), x1 f(x1), etc. xn f(xn). This polynomial Pnx is called the interpolating polynomial and x0, x1, etc. xn are called the nodes. If Pn is used to get the values of f for x's between x0 and xn, the process is called interpolation. If it is used to get the values of f outside the interval x0 less than or equal to x less than or equal to xn, the process is called extrapolation. According to Weierstrass approximation theorem, a continuous function defined on a closed interval ab can be approximated by a unique polynomial Pnx with any desired accuracy. Even though different methods will suggest different forms of approximation polynomials for a given data, according to existence and uniqueness theorem, they must give us the same polynomial. These polynomials may be expressed in different forms suitable for different purposes. We will study four types of interpolation polynomials which are computed from unequally spaced nodes and equally spaced nodes. Lagrange's interpolation polynomial and Newton's divide difference interpolation polynomial falls in the first category, and Newton's forward or backward difference interpolation polynomial belong to the second category. Here is the graph of a third degree polynomial which passes through the four data points between x is equal to 1 and x is equal to 9. Since we have the continuous polynomial function p3x which passes through these four data points, we can evaluate the function in between x is equal to 1 and x is equal to 9. That will give an approximate value of the unknown function. For example, suppose we want the function value at x is equal to 1.5, then we can directly substitute into the non-polynomial p3x and evaluate p3 1.5 and so on. So this is the idea behind interpolation. Newton's forward and backward difference interpolation formulae. In order to derive Newton's forward and backward difference interpolation polynomial, we require two operators called forward difference operator delta and backward difference operator del. First we define what is a forward difference operator. Suppose the values of unknown function fx are known at regular intervals with equal spacing say h. Then we can write x's as x0, x1 is equal to x0 plus h, x2 is equal to x0 plus 2h, etc. xn is equal to x0 plus nh. Let us define the first forward difference of f at xj by delta fj is equal to fj plus 1 minus fj. That means we move one step forward from fj and evaluating fj plus 1 minus fj. That number is taken as the first forward difference of fj. The second forward difference of f at sj by delta square fj is equal to delta fj plus 1 minus delta fj. That is the first difference of two first order differences. Then that will give the second difference at fj. And continuing in this way, the kth forward difference of f at xj is defined by delta raised to k of fj is equal to delta raised to k minus 1 of j plus 1 minus delta raised to k minus 1 of fj. That is, the kth forward difference of fj is the first difference of two k minus 1 order differences. And this is true for k is equal to 1, 2, 3, etc. In order to illustrate the concepts of forward difference and computation of higher order forward differences, consider the data points 190146, 1911 66, 1921 81, 1931 93, 1941 101. So the suffixes are j is equal to 0, 1, 2, 3, etc. up to 4. So In the second column, the x values are given, third column function values are given, and the fourth column is the first forward difference of different function values. We take the difference 66 minus 46 and writing this answer in the middle of the first and second row. Again 81 minus 66, the answer is 15, that is written in the middle of 81 66. 93 minus 81 12, 101 minus 93 8. So these numbers 20, 15, 12, 8 are called the first forward difference. So this 20 is the first forward difference of 46, 15 is the first difference of 66, 12 is the first difference of 81, and similarly 8 is the first difference of 93. In order to see this pattern in these higher order differences, we are writing the difference in the middle of the computing numbers. Okay. Similarly, the second difference is the first difference of the first order differences. Subtracting 15 minus 20, writing the answer in the middle of 15 and 20, that is minus 5, 12 minus 15 minus 3, 8 minus 12 minus 4. So these columns are the second order differences. Similarly, third difference is the first difference of second differences, that is minus 3 minus 5, that is 2, writing in the middle, minus 4 minus 3 minus 1. And finally, the fourth difference is the first difference of third differences, minus 1 minus 2 minus 3. Now, after completing this computational higher order differences, we can see a pattern in the higher order difference table. The first difference and higher order differences of 46 will lie in a forward sloping straight line. 20 minus 5, 2 minus 3 are the first difference and higher order difference of 46. So this 20 is the first difference of 46, that is, this is delta 46, that is delta square 46, that is minus 5, delta cube 46 is 2, and delta raised to 4 46 is minus 3. Similarly, the next forward sloping line 15 minus 3 minus 1 are the higher order first difference and higher difference of 66. 12 minus 4 are the higher difference of 81, and 8 is the difference of 93. So this table is called diagonal difference table, and we will use this diagonal difference table in the computation of forward difference interpolation formula and backward difference interpolation formula. Similarly, we can define the backward difference operator, where the function value is defined at equally spacing nodes x0. The second node is x1, which is written as x0 plus h, x2 is equal to x0 plus 2h, etc. xn is equal to x0 plus nh. Remember that in this Newton's forward and backward difference interpolation, we are considering only the nodes which are equally spaced, and the equal spacing is suppose h. Then using that h, we can write any node xn as x0 plus nh. So this x0 is taken as the reference point. Let us define the first backward difference of f at xj by del fj. Del fj is equal to fj minus fj minus 1. The second backward difference of f at xj by del square fj is equal to del fj minus 1, and continuing in this way, the kth backward difference of f at xj by del raised to k fj is equal to del raised to k minus 1 fj minus del raised to k minus 1 fj minus 1, and this is true for k is equal to 1 to 3, etc. That means the kth order backward difference of fj is the first backward difference of two k minus 1 order differences. Again, we are considering the same table, diagonal difference table, as discussed in the forward difference table computation. We are using the same function values, and the numbers are same, but the interpretation is different. See, if you are subtracting 66 minus 46, that number is 20, and this 20 is the first difference of 46, or this can be interpreted as the first backward difference of 66. How we will define the first difference of 46? First difference of 46 means we move one step forward and subtracting. That means 66 minus 46. If it is the first backward difference of 66, we move one step backward and subtracting. That means from 66 we move one step backward and subtracting. That is 66 minus 46. This 20 is the first backward difference of 66 or the first forward difference of 46. So all the numbers are same, but interpretation is different. So we can see that the fourth columns are first backward difference of 66 and 81, 93, 101, and the next columns are the again backward difference. So this is the backward difference of 15 minus 20, that is minus 5. Second backward difference is 12 minus 15, that is minus 3. 8 minus 12 minus 4, again minus 3 minus 5 2, minus 4 minus 3 minus 1, minus 1 2, that is minus 3. Now we can see a backward sloping straight line, that means backward sloping line in which the differences are written. So this 8 minus 4 minus 1 minus 3 are the higher order difference of this 101. So this 8 is the first backward difference of 101. This is second backward difference of 101, third backward difference, and the fourth backward difference of 101 is minus 3. Similarly, the next backward sloping line 12 minus 3 2 contains all the higher order backward differences of 93. 15 minus 5 are the higher order backward difference of 81, and 20 is the backward difference of 66. So we can construct the backward difference or forward difference table, but we can use different notation. That means we are computing the same numbers, we are writing the same numbers in the columns for first difference, second difference, third difference, and fourth difference, but according to our use we can interpret these numbers accordingly. Next we can consider the Newton's forward difference interpolation polynomial. See, we are considering the same data as before. That means we are considering the equally spaced nodes x0, x1 is equal to x0 plus h, x2 is equal to x0 plus 2h, etc. xn is equal to x0 plus nh, where h is the equal spacing. Then let us interpolate the function fx between x0 and xn, where the evaluation node x is equal to x0 plus rh, so that r is equal to x minus x0 divided by h. Then the function Newton's interpolation polynomial is approximating the function fx as fx is approximately equal to Pnx, that means that is an nth degree polynomial, is equal to f0 plus r into delta f0 plus r into r minus 1 by 2 factorial delta square f0 plus r into r minus 1 into etc. into r minus of n minus 1 by n factorial delta raised to n f0. See, the every terms in this Pnx are in this polynomial are, this is constant polynomial, this is a first degree polynomial, r into r minus 1 to product of two linear factors. So this is a second degree term, this expression contains a second degree term, and etc. The last term in the numerator we can have r linear factors multiplied together and multiplying with the delta raised to n f0 and dividing by n factorial. So ultimately the last term is an nth degree polynomial. So this Pnx is a polynomial of degree n or less. So this Pnx is called Newton's forward difference interpolation polynomial if you are choosing the reference point as x0. So the evaluation point, that means if you are interpolating the function at x, we can write that x in terms of x0 as the reference point x0 as x is equal to x0 plus rh. Then find that r is equal to x minus x0 by h. Using that r, compute a different linear factor product and multiplying them with the first difference, second difference, etc. higher difference, and dividing with the corresponding factorial. And usually this formula is used to interpolate or to extrapolate near the beginning of a set of equally spaced data points. Here this x is, if this r is positive, this x will lie to the right of x0, and if r is negative, this x will lie to the left of x0. If it is lying to the left of x0, that process is called extrapolation, because our data points is starting from the node x0 and ending at xn. If you are computing the function values in between this x0 and xn, it is called interpolation. If you are going outside this interval x0 xn, it is called extrapolation. Consider one example. Compute cos h of 0.56 from the following table using Newton's forward difference interpolation formula. So we have given 4 data points, 0.5 with hyperbolic cosine value 1.27262, 0.6 1.185465, etc. at 0.8 1.337435. Now for these 4 data points we can compute up to third order forward differences, and the differences are Subtracting the pattern 1.185465 minus 1.27626, writing the answer 0.057839 in the middle of these two function values. Again 1.255169 minus 1.185465, the answer is 0.069704. 1.337435 minus 1.255169, answer 0.082266, written in between these two numbers. Again the second order difference is the first difference of delta Fj, 0.069704 minus 0.057839, answer is 0.11865, writing in the middle. And completing this diagonal difference table, we can see the forward difference, the forward sloping in the forward sloping line that will contain the all higher order differences of 1.27626 with the first difference, second difference and third difference of 1.27626. If you are moving along the second forward sloping line, that will contain the higher order difference of 1.185465, and this is the first difference of 1.255169. 0.082266 is the difference of this number. Now our evaluation point is x is equal to 0.56 and reference point is 0.5 and h is equal to 0.1, because we are interpolating the function in between these two numbers 0.5 and 0.6. So this is the reference point. The spacing between 0.6 and 0.5 is 0.1. So h is equal to 0.1. Now using that we can compute the value r is equal to x minus x0 by h. After substitution we can see that r is equal to 0.6. Now we can approximate the hyperbolic cosine value at 0.56, that is f of 0.6, f of 0.56 approximately equal to P3x given by Newton's forward formula, f0 plus r into delta f0 plus r into r minus 1 by 2 factorial delta square f0 plus r into r minus 1 into r minus 2 by 3 factorial delta cube f0. Substituting for the function values and higher order difference at f0, that is what is f0, 1.27626, and higher order differences, and substituting for the linear factors r minus 1, r minus 2, and simplifying we will get the hyperbolic cosine value approximately equal to 1.160944. By the actual computation we can see that this hyperbolic cosine value at 0.56 is 1.16094078, and we can see that the exact value is agreeing with the value given by Newton's forward formula up to 4 decimal places. Newton's bicube difference interpolation formula. Using the same set of data which is equally spaced with the spacing h, so that x0, x1 is equal to x0 plus h, x2 is equal to x0 plus 2h, etc. xn is equal to x0 plus nh. We are considering the reference point as xn, and we are interpolating in between this x0 and xn, and that x is equal to, in terms of xn we can write that x is equal to xn plus rh if you are choosing xn as the reference point, so that r is equal to x minus xn divided by h. Then the function, the unknown function fx approximately equal to the nth degree polynomial pnx equal to fn plus r del fn plus r into r plus 1 by 2 factorial del square fn plus etc. plus r into r plus 1 into etc. r plus n minus 1 by n factorial del raised to n fn. See here the difference is because the reference point is xn, we are considering the function value fn and their higher order bicube differences, and the linear factors are r plus 1, r plus 2, etc. That means in the forward formula we are using the linear factors in the order r minus 1, r minus 2, etc. But in the bicube formula, if the reference point is xn, we are using the linear factors in the order r plus 1, r plus 2, etc. So the first term contains the constant term, that is fn. The second term is the first degree polynomial r del fn, r into r plus 1, product of two linear factors and multiplying with some constant. So this is a second degree term, and the last term will contain n linear factors in the numerator and multiplying with the constant. So this will constitute the nth degree term of the polynomial pnx. So pnx will be a polynomial of degree less than or equal to n. Usually this formula is used to interpolate or to extrapolate near the end of a set of equally spaced data points. Example, consider f of 1.92 from the following table using Newton's backward difference interpolation formula. So here we have 4 data points which are evaluated at 1.7, 1.8, 1.9 and 2. They are equally spaced with the spacing h is equal to 0.1 and some function values are given. And using these function values we are constructing a diagonal difference table. Here the differences are, we are interpreting these differences are backward differences because we are using Newton's backward difference interpolation formula. So subtracting in the pattern 0.3399864 minus 0.3979849, the answer is minus 0.0579985. Placing that answer in between these two function values and continuing like this, we can compute all the higher order differences. And here we can see the sloping line, that means the backward sloping line, and along which all the higher order differences are written. So they are the higher order backward differences. So this red pattern, that means this red pattern indicates the higher order backward differences of the function value 0.2238908. So 0.2238908 with the first backward difference is the number minus 0.0579278. Second backward difference of 0.2238908 is this number, and third backward difference of 0.2238908 is 0.0004093. Similarly, we can move along another line. Along this line, these are written as the higher order backward difference of 0.2818186, etc. Now our evaluation point is 1.92, which is nearly equal to near the point 2. So we are taking this 2 as the reference point, xn, and the spacing is equal to 0.1, and r value is equal to x minus xn divided by h is equal to minus 0.8. Now the function value f of 1.92 is approximated by the third degree polynomial P3x given by Newton's backward formula f3 plus r del f3 plus r into r plus 1 by 2 factorial del square f3 plus r into r plus 1 into r plus 2 by 3 factorial del cube f3. Substituting for r, f3 and higher order difference of f3 and simplifying, we get f of 1.92 is equal to 0.2702005. And here the tabular values of the unknown function are actually the Bessel function J0x, and on actual evaluation, direct computation, we can see that J0 of 1.92 is 0.270201. And that value, that means the exact value of J0 1.92 is 0.270201 is agreeing with our value given by Newton's backward formula up to 4 decimal places or 5 decimal places, 0.270201. This is the way in which we are interpolating the given data points using Newton's forward and backward difference interpolation polynomial. Thank you.